on recurrent neural networks. I'm Vedant, and me and David are taking the recitation. So, so we had a lecture on recurrent neural networks, and Diksha went over like why RNNs are important, why memory is important, why a simple MLP does not do jobs such as sequence prediction. So. So what we'll be covering today is basically basically an overview of RNNs in PyTorch, how RNNs can be used in a language model. So RNNs have a lot of features with them attached to them in PyTorch. So we'll be going over all of them today. And especially variable length inputs, that's something that you should pay attention to because this is going to be important for homework 3 and homework 4. So what is an RNN? An RNN, as you can see over here, so this is basically the computation of RNN that is unfolded in time. As you can observe, there is an input that's given in the green circle, that's X. The hidden states. So the standard representation for RNN is as shown in the left-hand side. We have the loop. There is a loop symbol that basically shows that the units are being repeated, and each unit, each cell basically produces an output based on an input. And when you unfold it in time, as you can see over there, you have at time t-1 for the t-1th input, you have the output at that time. So each time, basically, you step through time, and at each time you'll be generating output. That is basically how you model the sequence using an RNN. So RNNs are hard to train. They present challenges that are different from networks like MLPs or CNNs because of the fact that RNNs look in the past and sometimes also in the future. So RNNs suffer from saturation. They suffer from vanishing and exploding gradients. Can you think of why RNNs would face from like vanishing and exploding gradients? So basically, exploding gradients is something like your gradients keep accumulating as you propagate through time, and then suddenly all your gradient values are just none. Or vanishing gradients in this case is, your over time your gradients they start tending towards zero. So could you think of why RNNs suffer from this problem, vanishing and exploding gradients? Yeah. So basically, what backprop through time does is you're accumulating gradients as you move behind in time. So what that does is over time you'd be either you're accumulating gradients as you keep stepping. The further behind in time you step back, the more you'll be accumulating the gradients. It's the same logic for vanishing gradients. So that is a big problem with RNNs and something that you will likely be facing in your homeworks. They have complex loss surfaces with lots of bad local minima. They don't usually like dropouts. Now, dropouts are something that you have encountered before. You might have used it in your homeworks too. And the fundamental, like the way dropouts work is they randomly drop some neurons, and then it's basically like a regularization method. Could you tell me why dropouts don't work with RNN? Just in this image, for example, if I had to put a dropout between each of the LSTM cell, right? At each time step, I put a dropout that basically the input is the previous time step, and then it goes into the cell that is at the next time step. So could you tell me why dropouts don't work well with RNNs? Okay, so here's the thing. So the input to any RNN cell at a given time is not just the current input. That is that what I mean to say is, like, for example, if you have the hidden cell HT, the input to that RNN is not just XT, but it is also the previous hidden state. So you have a memory that comes in from the previous time step. Now, if you're putting dropouts, what you're effectively doing is you are dropping that memory, which you don't want that. You want the entire you want the memory as it is when it comes from the last this one. So basically, each time you run dropout, you'll be having different basically you're dropping different paths from the previous time step, which is not good. That is kind of you're telling a network that that some parts at one epoch this part is important, this epoch this part is important. So that's basically it's not going to work well with your RNNs. So to counter this, towards the end of this recitation, I'm going to link a paper. That is something. There are different types of dropouts with RNNs, like log drops, weight drops. They are specifically designed to work with RNNs, and something that is important for you to know when you're doing your homework 3 and homework 4. So LSTMs and GRUs were made to address some of the issues, like for example with vanishing gradients. But then these issues still occur, and then you still have to spend your time trying to debug and get around these issues. Now, this was something again that was taught in the class, that RNNs are used to address different types of tasks. You can have one-to-one, you can have one-to-one sequence generation, you can have one-to-many, you can have many-to-one, many-to-many, and I'll go over these one by one, what each of them mean. So, like for example, one-to-one is just a simple MLP, right? It's just you are not taking anything from the previous inputs. It's just a direct feed-forward network, like the MNIST classification example. And then you have one-to-many, where basically you have one input to the entire RNN sequence, and you are generating a whole sequence out of it. For example, you have image captioning. This is a really popular task. Like you can see over there, the man in black shirt is playing guitar. And you can kind of see how this works. You have one input that is like the photo of the man playing the guitar, and you need to generate a sequence that comes in the order, like the first it's the man, and then the black shirt, and then it's the guitar. The ordering over here is important, which is why we use an RNN. If, for example, the output generated by RNN is something like the guitar in the black shirt is playing the man, it's not correct. So. Then you have many-to-one, for example, which is sentiment analysis. That could be an example where you have an entire sequence, like for example, driving to Disneyland was fun, and then you'll be giving the sentiment of the sentence, like like was it positive, was it negative. That's a good example for many-to-one. And then you have many-to-many. That is machine translation is a very popular example for many-to-many. Where basically, if you notice, you have a English sentence. For example, I bought a sweet person in a store, and then you convert it to German. Now, it is important to note over here with many-to-many that it's not always necessary that you have a one-to-one correspondence. For example, if you notice, the English sentence has say it has like how many ever words. It's not necessary that the output sequence is a one-to-one correspondence. Like I is always, in this case, okay, I is connected to ik, but then it's not always necessary that there will always be one word is corresponding to the output word. So the ordering can change. The RNN should learn how to do that. So I'm going to go over the first, the key topic of today's recitation, that is language models. So what exactly is a language model? Language models are basically they tell you how likely a sentence is to be well structured. Like there is so there are different types of language models. In traditional natural language processing, you have unigram models, you have bigram models, you have trigram models, and so on. So basically what they say is how likely, for example, the example there is the dog barks, the cat meows, the wolf howls. That's obviously correct. The last one is, as you can clearly see, it's not. So this is basically done by attaching a probability to each possible sentence, right? But you can kind of already see why this is not so efficient, because then you need to have a complete probability distribution over all the words in your corpus, right? So this is where RNNs can be useful for modeling a language. Now, for example, if you look over here, so you have the sequence, the students open there. Your RNN kind of models it. It has the initial state at 0, and then you have the inputs to each time step. At H1, you have at H2, you have students open there. So on, you feed the inputs to RNN. And then now the final output of the RNN is it should generate a probability distribution over all the possible words that it can generate. For example, books will have a high probability based on whatever corpus it was trained on. Laptops has a high probability. Zoo is definitely not, like, it's low probability, right? You can, the students open their zoo is not correct. So this is how an RNN models a language. Uh, and so this is an so RNN is, so you can the library for using RNNs with PyTorch is torch.rnn, and the module in this case, a typical RNN, whether it is LSTM, GRU, or just a simple RNN, so it follows the input size, that is the number of neurons at the input, or the number of features at your input. The hidden size, that would be the number of neurons in your hidden layer. You have the number of hidden layers, the batch first, and it's important to note over here that PyTorch is a little weird with the way it handles the dimensions for RNNs. If you can see over here, the format of the input is sequence length cross batch size cross input size. Usually for your MLPs and CNNs, the batch size always comes first. But in the case of RNN, they have this weird, the weird way where they put batch size as the second dimension. So if you want batch size to be a second dimension, if you're okay with it, you can keep batch first as false. But if you want your batch size to be the first dimension, then you put set batch first equal to true. And the reason why I specify is because we have this is a very common source of bugs in your program. Like a lot of times your model just does not generate properly, or you have dimensional errors, and then people, they just miss out that not set batch first. They set batch first as true, for example. And then so if you observe the output, so the input is of sequence length cross batch size cross input size, and then the hidden size, the output of the hidden state is number of layers cross batch size cross hidden size. So here is okay. So it is important to know that the output of an RNN is basically the output of the final, it's the hidden state of the final layer of the RNN. So you can have like 4 or 5 layers, for example. The output that like if you do nn.lstm, the final output is basically the output of the final layer. Now in the case of an so basically the size of the output will be sequence length, comma batch num, comma number of directions into the batch size. So in this case, if it's a unidirectional RNN where you are only propagating through one direction, like you go from the past to the future, then you'll have number of directions of 1, in which case your final size will be just hidden size. But if you have bidirectional RNN, for example, where it's both forward and backward, then your total size will be it will be hidden size into the number direction. Now it is important to know that LSTMs and GRUs have a slightly different format in the output. So they have this thing called hidden states and memory cell. So to explain this, you can just have a look at this diagram. So so you have each of the RNN cells that is described over there. And then you have the initial hidden states and the cell states basically. So when Bhiksha will teach you this in the class, LSTMs and GRUs, you'll notice that they have different, like there is so there are different cells in the LSTM and GRU. So basically you'll be maintaining the states for each of that. So PyTorch preserves the hidden values and the cell states. So you'll be propagating through time. The output is basically the hidden values at the final layer. And then you can also extract the hidden values and the cell states for each of the layers if you so wanted. And so sometimes it's useful that instead of defining an entire RNN layer where one layer comprises of many different RNN cells, you can define one cell at a time if you want to customize it. If you have an idea of customizing it, you can add like dropouts between each of the cells. So for that you can declare PyTorch provides you this module called RNN cell. Right. So so what goes into your, so you obviously can't feed words directly into your neural network, because strings don't make any sense to a network. It has to be something. So basically what your network takes in is a vector, right? So to convert a sentence or or any corpus of text into a vector, you basically use the embedding layer, where the input to the embedding layer will be your your corpus, for example, and then it's going to generate a vector out of it. That is done at the embedding layer. And so now, so to train a language model, initially you can, so you will have a big corpus of text. You need to decide how it goes into your RNN. So the most simplest way is, you just fix, like for example, you have a giant Shakespearean text, right? You have the entire, say, the Julius Caesar play. Now you want to feed this into your network. So what you do is you decide a sequence length of, say, 5 words. You'll chunk up your entire corpus into like five words. You feed each of them into your embedding layer, and whatever is generated at the end, you're going to pass it into your neural network. And this is important to know that even if you are training on a fixed size, for example, every time you are like, say you generate like, you are always feeding it 5 words, your neural network shouldn't always generate 5 words. It should be capable of generating a variable output, right? So how do you evaluate a RNN model? So a good way of evaluating it is something called as perplexity, where perplexity is basically like, it's as defined over here, like if for example, so if you have a perplexity of 100 as it is defined over here, so basically the perplexity of 100 means that each word there is like a possibility of 100 different words for it, instead of that one word. For example, if you're generating the dog barks, right? So the word barks has a low perplexity because you know that barks is what should follow a dog. But if for example, you have the dog and then you could have anything after, the dog eats, the dog sleeps, the dog, so there could be many words after that. So now, putting all of this together, so the way you would generate is that, till now what do we have? We have prepared the input, we have chunked them into fixed sizes, we pass them into RNN, we have an evaluation method like perplexity. But how do you actually generate from, so now the output of your RNN is basically like a probability distribution, right? You have probability over all the possible words. So for example, if the input was the dog, then barks will have a high probability, meows will have a low probability. So how do you actually generate a sentence from that probability distribution? One very like a very bad way is that you go over all the possible sequences. You generate everything possible and then you compute the probability of each of them. You can kind of already see why that is inefficient. If you have a large corpus of text, you're not going to spend all of your time going over all the possible sequences that could be generated. So instead what you do is you use algorithms like, there is obviously greedy search, where you kind of select what is like the highest probability at each time step. You could do random search, where based on the entire distribution of the entire distribution of the output words, you sample what is the most likely sentence. You have beam search. This one is quite popular, and this will be covered in the next recitation. You will be going over. You'll be going over the n best words, and then you'll be maintaining a beam width of that. So so how do you actually train? Okay, so for training a language model, it is important to know that initially I talked about that we always keep a fixed sequence length. Like you always have 5 words that you're passing into your RNN. But this is not always the case, and if you're always going to send in if you're always going to send in a fixed sequence into your RNN, you're not always going to get the best results. So so that is why your RNN should be capable of handling variable length inputs. Now, like for example, like I like apples, jamais les pommes, and then your input is 3 words and your output is like what is. So then your RNN should be capable of dealing with different words. So and now again, this is another important concept that you should know, because dealing with variable inputs is something that gives the most grief, especially for like homework for, I don't know, like there is a lot of issues that people face with with how to deal with variable inputs. Sometimes they don't pad correctly, they don't pack correctly. I'll go over these right now, but it is important that you pay attention to this part. So so now PyTorch provides two different modules to allow for padding and packing. I'll go over what packing means. Padding is something you all already did. This was in your homework 0, where basically if you have, it makes intuitive sense, where it's like if you have variable inputs, you just pad all of them to a constant length and then you pass it into your network. So now PyTorch provides a module called as pad_sequence, where basically what you do is, now for example, look at the example down below. So you have like you have torch.stack of x1, x2, x3, where x1 is 1 comma 2, x2 is 4 comma 2, and x3 is 3 comma 2. If you stack all of them together, it's obviously not going to work because they are both, all of them are of different dimensions. And notice how this follows the sequence. So the typical input dimension is sequence length, batch size, and input size. As you can see over, sequence length and input size. So these inputs, basically the input size is always the same, but the sequence length is different. That's obviously the case, right? So now what pad sequence does is, if you pass it through pad sequence, it pads zeros to all of them in such a way that that all of them are basically of the same length, and now you can pass it into your network. So oh, and there is also the term. So it's again important that you keep track of your batch. Because if while you declared while you initialize your RNN with batch first equal to false, and then suddenly over here you put batch first equal to true, and again somewhere you have batch first false, you are going to get confused, your code is going to get messed up. So please keep track of the way your output sequences, the shapes of your output sequence. So and then there is pack sequence. So now once you pad your sequences with all the zeros, it is important to understand that there is going to be a lot of redundant computation, because you basically, when you're computing the, for example, you're computing the loss, or when you're even if you're passing it through the LSTM, you don't actually want to compute over these zeros. All these zeros do is they just basically, you're padding all the zeros. So for example, if you want to stack all of them together, so then you're padding all of them. But when you're actually computing it, you don't actually need to compute over all these zeros, right? That's just redundant computation. So what you do is, PyTorch provides this method called as pack sequence, where basically what it does is it allows you to kind of keep track of what are the actual inputs in your network and what are the padded inputs to your network, right? So this is so what if you pass a pack sequence into the network, what this basically does is, now you can the computation only happens across all the actual input lines. It kind of ignores all the padded zeros. So and again, it is important to note that pack sequence has got two fields over here. One is enforce sorted, and one is so enforce sorted is important because sorting related bugs are some of the hardest to find. If you're not keeping track of this, sometimes the order in which your inputs come, your outputs generated, they can be messed up. So if you're not, so it is important that you ensure that that your sorting is that. I would usually recommend that you keep your sorting as false, but then that is, if you're keeping it as true, then you should be aware that that you are sorting through your inputs. Like lot of the bugs are generated because people don't have any idea whether the network is sorting or if it's not sorting, right? So you should keep a track of this. And then there is also pack padded sequence and pad packed sequence. They basically they're all the same. So basically what pack padded does is it packs a padded sequence, and pad packed is it pads a packed sequence. I know this is all a little confusing, but David is going to go over the recitation code, and in the recitation code each of these are used, so you can kind of get a better idea of how it's used in the code. So this is the way it used, and then you would probably understand it better when you just see it in code. Right. So it is important to understand that MLPs, RNN, CNN transform, all of these are just like feature extractors. It is shown that temporal convolution networks, they outperform classical LSTMs in this. So the paper is linked if you want to read it. And this is an interesting comparison between RNN and CNN. And actually, if you observe, this is actually interesting difference between RNNs and CNNs. Is something you can probably use in your homework for. Is that if you observe over here, RNNs take an input sequentially, whereas CNNs consider the entire. They basically consider the entire sequence at a go. Right, so then if you know like CNNs then make like really interesting feature extractors. So if you can think of a paradigm where where you put CNNs at the input, like like the input is passed to CNNs first and then it is put into RNN. So not only is your not only are your like your RNNs modeling the sequence, your CNNs are also extracting the features from your entire sentence instead of like going over it one sequence at a time. So yeah, so there is also like concepts that can be attached to RNNs, for example, like attentions and transformers. All of these will be we'll be going over in future lectures and recitations. And so please do read through this paper, Regularizing and Optimizing LSTM Language Models. You'll be using this in your homework 4 and actually in homework 3 also to get good results. Because tuning your LSTM networks is it's really difficult. So it's good to read through this paper. You'll have different dropouts, for example, what are the best ways for optimizing LSTM. Attention is all you need is a really popular paper, so you can go to that also. And now David will pick up the code.
Testing. Can you guys hear me? Okay. So, all right, I guess I have to look at the screen. Okay. So basically, in this notebook, there are two main examples. So the first example is with fixed length input, so where every sequence length is equal. And in the second example, we'll be talking about variable length input. So in the fixed length input, what we're doing here is we're setting up a Shakespeare language model corpus, and all this code, wait, let me scroll down a little bit. This code is just reading in everything from this specific corpus of Shakespeare, dividing it up into equal size sequence lengths defined by SEQ lang or something, and then converting everything into indices. So we also set up a dictionary from every character A, B, C, D to a number. So we're translating every sequence length into a series of numbers representing that sequence. That's what that's doing. Okay, so this is the data set that sets up the actual data set that you're going to train on. And the first thing that it's doing is it's taking the length of the entire text and dividing it by sequence length. And you can see that it's a double divide because we're just going to cut off anything that doesn't evenly fit into our sequences. And then it's basically putting together all the different sequence lengths into a big tensor. And when we ask for a specific item from the data set, if we ask for the ith element, we get the ith sequence. And we already know that it's a fixed sequence. And the purpose of this example is to predict the next character. So if I draw a quick example, suppose this is your input. So A, B, C, D, E. And then you want to feed that through an RNN. And then for every time step, it predicts an output. And the goal of this RNN is to predict what comes after A. So ideally, after reading in A, the RNN would say, oh, what comes after is B. After B, C, D, E, and after E, F. So to get this training data, so these are the inputs and these are the outputs, we actually need a little more than just a length 5 vector. We actually need a length 6 vector. So our actual training example, or the sequence length that we split up into, is going to be A, B, C, D, E, F. And we're going to feed the first 5 inputs into the RNN, shift it over by 1, and then expect it to predict the last 5 inputs. So that's what the return text -1, comma text 1 is. So the training inputs is everything besides the last element, and then the testing is everything from the second element to the last element. So everything's shifted. So you need to keep that in mind when you write your own data set. Collate is a function that takes in a list of these training examples, so the training and target pairs, and then puts them all into a batch. So basically what this is doing is, if we have a bunch of these, it's just stacking them into batches. So it's going to be batch size by sequence length. And that's all that's doing. Now to actually get into our model, you briefly got an explanation for what embedding is, but I'll go through that really quickly again so you know exactly what's going in and what's coming out. So suppose you have a vocab size of like 100,000 words. In this example, it's on characters, but you can also do it with words as well. So if you have 100,000 words, it's not really realistic for your model to like recognize all the 100,000 words. There's just not enough storage space. So what you want to do is take those 100,000 words and collapse it into a tighter representation. So that's what the embedding layer does basically. So car would become some kind of vector, and the length is called the embedding size, and you decide what the embedding size is. So car would be embedded into some vector of size, let's say E. So would truck, and so would person. And the importance of this layer, in part, is that the embedding that it learns is actually semantically relevant to the actual words. So you would expect that the embedding for car and truck would be more similar than car and person, and that really helps the model learn. So in essence, embedding takes in a vector, or if you put in a single number, like 0 for representing car, 1 for truck, it spits out an entire vector of length E that you specify, called the embedding size. So we define our vocab size. In this example, we're just doing characters, so I believe it's 26. Embedding size, we just explained. The hidden size is the size of the hidden layer in your LSTM. And number of layers in your LSTM. Embedding, we actually make the embedding layer. And lastly, our RNN has input size corresponding to embedding size, because we'll run individual characters into the embedding, get a vector of length embedding size, and then directly feed that into our LSTM. So the input size needs to be our embedding size. Then hidden size, then the number of layers. And the last layer is a scoring layer, because after you run your input to the LSTM, the last layer of the LSTM is going to output a vector of size, hidden size. From that, we want to predict what that character is. So we have a linear layer that goes from hidden size to vocab size, and the final output is like a probability distribution that tells you what the final character is. One thing you can try moving forward on homework 3, actually homework 4 I think, is tying the embedding layer with the final linear layer, but for specifics you can look at the documentation. Okay, now let's go through the forward. So the sequence batch that we pass in is, it's almost this, except it's flipped. So it'd actually be a tensor of size sequence length by batch. As for why we put it in this format instead of the other one, I have no clue. You can do it either way. LSTM takes a batch first argument that you can specify. So it takes in sequence length by batch input, and then runs that through an embedding. So right now what we have here is a tensor of indices, each representing a character in this case. And then if you run that through the embedding, for every index in the original tensor, you're going to get a vector of embedding size. And that's how you end up with sequence length by batch by embedding size. And then you want to run that through your LSTM. Well, actually, you want to run that through your LSTM. That changes the last dimension, which was previously the embedding size, to the hidden size. And the LSTM actually spits out two inputs. The first in the tuple is the actual output of the final layer of the LSTM. And then the second of the tuple is actually another tuple that has the cell state and the hidden state. As for what exactly the cell state and the hidden state is, it will be covered in later lectures, but it's basically the current memory of the LSTM that gets passed through for every sequence. Oh, also, I want to clarify. In lecture, we talked about passing each word or character to the LSTM at a time, or the RNN at a time. But in PyTorch, you can pass the entire sequence, and it takes care of the looping through time for you. Lastly, after we get the output from the LSTM, we flatten it. So, because basically what it outputs is a probability distribution for every position in the sequence and batch. Technically, these two don't really matter for training because we're not generating anything yet. So we just collapse everything down to, we collapse these two dimensions. So we'll just have a long vector, and at every position in the vector, we'll have another vector, and that's the probability distribution, or the logits from previous sections. And then I believe, do we directly output that? Oh yeah, we have to pass that through the scoring layer to get the probability distribution, and then we reshape it back into sequence by batch by now the vocab size. If that was confusing, we'll upload this Jupyter notebook and then a more detailed one with a lot of comments explaining that, so you can reference it. Now, since we trained our model, we also want to generate some stuff to it. So the main point of generation is exactly this as follows. So, but you wouldn't actually have any of this. So if you start with some series of input, let's say A, B, C, and then you run that through the RNN, and then you generate a series of outputs. Ideally, this would be B, C, D. But this is all the input you get, but you want more. So you take the final output that your LSTM outputted after the input sequence. So semantically, this would be after A, B, C, your RNN thought D came next, which is correct. Then you take that as your input for the next time step. So the key point to note that is this isn't ground truth. This is something that your RNN generated looking at a limited amount of ground truth. So you take D, pass that into your RNN. Let's say it predicts E. Then you feed in E as input, and then your RNN might predict F, and then so on. So what ends up happening is after first input, your RNN is generating a series of outputs on its own, taking what it generated as a time step and feeding that into its input at the next time step. And this is what we call generation. And we can control how far this goes by either having a special ending character. So if your RNN outputs an end of line character that you specifically designate, then you'll be like, oh, we're done with generating. Or since this could potentially run forever, you can pass n words argument to generate, and it will just stop after generating n words. And there's a lot of code here, but basically to simplify it is, since you're only doing one sequence generation at a time, you're passing in a length L vector of initial inputs. You're working with the dimensions to make it look like a single batch, like a element, like a batch size of 1. You pass it through your LSTM, and then in the for loop, you take the last element, feed it in, and then keep looping through it. And then in the end, you have a generated sequence. As for specifics, you can go through the code, and we'll release the annotated version. Yeah. And now we just have the typical training loop. Everything's essentially the same except for one thing, which is, let's see, this line right here. So remember that our training and targeting pairs are this sequence and this sequence. But after you run this through the LSTM, you get a probability distribution over the size of vocab size for what each of the outputs may be. But just like any other classification tasks that you've been doing in homework 1 and homework 2, you just toss the outputted probability distribution and the true single target label to cross entropy, and then it will just take care of the rest for you. And then you just, yeah, this is exactly the same as you would do before. Training, for example, we just ran it. This is the actual generation. We've talked about this already. This is actually putting it in an outside function and taking some stuff from the corpus to run. And then, yeah, right now it's not doing too well because we didn't train it for that long. You'll end up, likely in your homework 3 and 4, you end up seeing like a lot of repeats, but this should get better over the epochs. Okay. So far, we've only talked about training RNNs for fixed length sequences. So every sequence that we trained on so far had a fixed length of like, let's say 20. However, this isn't the best way to train, like, because what ends up happening is you cut off a sentence in the middle where it doesn't really make sense to cut off. Maybe you want to train over sentences instead of characters of length 20. And that's when variable sized input comes in. And this is where you use the pad and the pact. So just for example, suppose your feature dimension for every point in the every time step in the input is just 1. So you just have a single character instead of some more features. And let's say your variable inputs are of size 3. Can you see this? Okay. 3, a little bit longer at like 4, and then 2. So internally, actually, as you talked about in class, the LSTM or the RNN processes inputs by one time step at a time. So, and the whole reason we have to worry about this in the first place is because of batching. To make things run faster, we would like to run multiple sequences at the same time. So the LSTM would like to look at the first one, move on to the second one by transferring the hidden state, second one, third one, and so on. But the problem is you can't just directly stack these because these are of different lengths. And one solution to solve that is by padding. So you pad the smaller sequences with zeros at the end to account for its shorter length. And in this scenario, even if it gets to the end of a shorter sequence, it can keep going by just using the 0 input. But as it was mentioned earlier, this has a lot of wasted computation because you're essentially plugging in zeros to your LSTM and just tossing out the input. And in worst case, you could end up doing a lot more work than you should, because if one length is 100 and the other two are like 2, then you're doing probably like batch size times work. So the alternative is packed sequences. I said earlier that the LSTM computes by time step. So these 3, oh, by the way, let me just write this. This is batch size. In this example, this is equal to 3. So these 3 are semantically linked because they are at the first time step. So LSTM will look at these first, and then look at the next time step, and so on. And the packed sequence takes advantage of this. So if we label this as group 1, group 2, the packed sequence actually has shape group 1, group 2, and a smaller group 3, and so on. So these are all the inputs over the batches for time step 1. These are all the inputs for the over the batches for time step 2 and 3. And you notice that the inputs for time step 3 are a little smaller than the other two because this sequence ended at time step 2. So for group 3, there's only 2. So this is length 3 because 3 batches. But then here it's only length 2 because only 2 of the sequences are still going at that time, and so on. So that's the general framework for how pad and pack work. There's a really nice diagram explaining this online, and we'll make a post on Piazza about it. So this, I believe, is just going through every line in the Shakespeare and splitting it by lines and not a fixed sequence. Lines data set. Yeah, in essence, this is very similar to, at least the lines data set is very similar to what we saw before, because even if the things are variable length, for every input, we still follow this format of the input being shifted to the left by 1 and the output being shifted to the right by 1 to offset it. As for the collate function is a little different. Oh, okay. collate function sorts the remember that collate function takes a list of sequences, and now these sequences are of different lengths. So this basically sorts the sequences by length, because to put it directly into packed sequence, you need to sort it in decreasing length order, and then outputs a list of inputs and a list of targets. And this is the actual packed language model. So the init is, I believe it's almost the same. Yeah, it's essentially the same. You have the vocab size, the embedding size, the hidden size of your RNN, the number of layers in your RNN, the embedding layer that we talked about earlier, the RNN itself, and the final scoring layer that maps the output of the RNN to a probability distribution. And then you also have this stop character. Remember what I said earlier about generation? You can either stop if you have a designated stop character or after you generate a fixed number of words. In this case, we have a stop character. Now for the forward. The forward becomes quite a bit more complicated. So what the top part of the code is basically doing is it's manually, okay, frankly, you can not do the top part of the code. As you can see, alternatively, you can use RNN pad sequence followed by RNN pack padded sequence. I strongly recommend using that instead of managing everything in your own. Because what the top part is basically doing is it's saving the lengths of this inputs, concatenating all the inputs, similar to this, running it through the RNN and unpacking it with the inputs with the lengths of the inputs you saved earlier, which is a lot of things to manage and can cause a lot of bugs. So I strongly recommend just padding the sequence, packing the padded sequence, running that through the RSTM, and then unpacking it, and then getting your actual output. And after getting the output from the LSTM, the rest is similar to above. You map it to a probability distribution, and then return the output. Lastly, for generate, I'm pretty sure this is exactly the same code as before. So we'll just go and skip it. And the training loop isn't any different because internally, it is a little different. So what the model actually returns is this after going through the LSTM. So at each of these positions, you have a probability distribution vector. And the model actually also, the data set is returned so that in the same format. So, but in the data set, you would have single labels. And label probability distribution, you can just put that into cross entropy. So the main thing to note when you're writing your own models, data set, data loaders, etc., is to keep track of, at least know what's going on with the lengths. So what happens, the reason why sorting before packing sometimes becomes a big issue is if you sort it, the total length, the sum of the lengths of the sequences don't change. So there's going to be no errors, but when you actually train it, you're training on totally different sequences. So this is the sorted, but if you had actually expected it to take this format, then you'll be comparing this with a totally different sequence, and your network won't learn anything. So if you feel that you don't have any bugs, but your network's not learning anything, the first thing you should check is the padding and the packing, and etc. And I forgot to mention this earlier, but one advantage of using the pad sequence, this zero padded format, is you can pass this to a convolutional network. So even in homework 3 and homework 4, before your RNNs, something you should try is passing the input to a convolutional layer, and then passing that to your RNN. So in this case, the convolutional layer would treat this as batch size 3. This is the sequence length. And then, in this case, the feature or the channel dimension is 1. But if you have more channels, that would be your channel dimension. And it's useful because you can easily adjust the channels that you're inputting. You can make it bigger or smaller and then feed that into your RNN. This is just setting up the data set and the data loader. This is training. And yeah, that's about it. Anything I should add, do you think? Yeah. So just, I guess, takeaways would be homework 3 and homework 4. Be careful with padded and packed sequences. Those are the source of probably most of the bugs you'll have for those 2 homeworks. Remember the shifting. So if you forget to do the shifting, then your RNN will just say, oh, what comes after A is A, B, B, instead of A, B, B, C, and so on. Just things to watch out for. For embedding, you shouldn't need for homework 3, but homework 4, you're going to definitely need embedding. And yeah, that's about it.